In the name of God, I welcome all the students and viewers to this channel. I am truly happy to share these videos with all A-level students, A-level, especially A-level physics students. This video is made just for you to help understand concepts better and to make learning physics easier and more enjoyable. So I want to clearly say that this is not about increasing subscribers or viewers. My only intention is to share knowledge and support you in your studies. Please remember, my only intention is to share knowledge and support you in your studies. However, to stay updated with all upcoming lessons and to follow the full series, I kindly ask you to subscribe to the channel and click the bell icon. That way, you will not miss any future videos. So grab your pen and notebook and let's begin our physics journey together. Last video, we discussed around 10 questions of the past paper A-level physics under units and dimensions. So we will continue the past paper discussion questions. That is question number 11. Okay, we will discuss about question number 11. The question number 11 is from the past paper 2001. Okay, what they are asking, electron volt, EVO, electron volt is a unit of power, energy, charge, voltage, or potential difference. Those are the options. So we have to know what is electron volt. 1 electron volt is the amount of kinetic energy gained or lost by an electron when it is accelerated through a potential difference of 1 volt. So it means it's about kinetic energy, energy gained. So the unit of electron volt is energy. By experiment, it's derived 1.602 into 10 to the power minus 19 joules. Okay, why not the others? The answer, others not the answer. Okay, so the power. What is power? Actually, power is work over. Power is what? Work over time. Work over time. It means by unit, what is that? Joule per second or joule second minus 1. Okay, by T. Okay, that's joule per second minus 1. Okay, so charge also measured in coulombs. That also not the unit of energy. Voltage are measured in volts, but also having units. It's okay. So the voltage measuring by 1 joule. Okay, 1 joule over 1 coulomb. 1 joule over 1 coulomb is the volt. Is potential difference. Potential difference also measured in volts. Also not the measure unit of energy. So these are the reasons. The other four are not the answers. So the answer is energy of electron volt is the unit of electron volt is energy. Okay, the answer is option number 2. Okay. Okay, question number 12 is, in the following expression, I and V represent currents. I and V represent current and voltage respectively. C is a constant. Okay, so they are asking about the term KT over Q is what? It's a dimension of what? That is the question. Okay, So this question we can do by two methods. One is understanding of this equation. Understanding of this equation's components, we can identify or derive the dimension of kt over q component, kt over q term. Okay. In other way, by the dimensional analysis also we can derive the kt over q terms dimensions. First, we will see by understanding the equation how we can derive the term of kt over q. This equation is c into logarithm of I over I1 plus 1 into is equal to QV over KT. QV over KT. Okay. So is derived from the Shockley diode equation. This is derived from the Shockley diode equation, which describes the current voltage characteristics of a PN junction diode in semiconductor in physics. Okay. So this is the equation is from the derived from the Shockley diode equation. Okay. Where I is the diode current, I naught is the reverse saturation current, a small constant. Q is a charge of an electron. Q is a charge of an electron. V is applied voltage across the diode. Okay, the K, small k is the Boltzmann constant. Boltzmann constant. And the T is absolute temperature in Kelvin. Absolute temperature in Kelvin. So by understanding this formula and this and the terms dimensions, we can derive the terms of KT over Q. Okay. So it means, okay. So we know that the Boltzmann constant, what is the Boltzmann constant unit is joule per Kelvin. Joule per Kelvin. The temperature is K. Okay. So what are the terms are here? K is here. In this, what are the terms are here? Small k T over Q is the term. Okay. By understanding the equation and the terms definitions, we can derive the terms of dimension of the terms of kt over q. So the k is, we know that is Boltzmann constant. The Boltzmann constant unit is joule per Kelvin. Joule per Kelvin. T is temperature, the absolute temperature in Kelvin, and the q is charge in coulombs. Charge in coulombs, we can say in coulombs. Okay. So saying by knowing that, we can derive that the term of kt over q dimension as like this. K is joule per Kelvin and into temperature also measured in Kelvin, and also C is a coulomb. So it means the term kt over q's dimension is equal to what? Joules per volt. Joules per coulomb. Joule per coulomb. Joule per coulomb. So joule per coulomb, we know that is volt dimension. Joule per coulomb is the volt dimensions. Why? The volt, what is volt? The potential difference between 2 points. The potential difference between 2 points when 1 joule of energy is used to move 1 coulomb of electric charge between those points is 1 volt. Is 1 volt. So the 1 volt is equal to, there is measuring 1 joule over 1 coulomb. 1 joule over 1 coulomb. So the term we derived, the term of kt over q's dimension also we derived as joule per coulomb. It is the dimension of volt. So by understanding the equation and these terms, we could derive the dimension, that is the dimension of volt. It's the option number 5 is the answer. Otherwise, if you don't know, the terms and the equation, still you can derive the dimension of the term kt over q by the dimensional analysis. That is how we will see. Okay. Let's say the equation is dimensionally balanced. The equation is dimensionally balanced, and the QV over KT must be dimensionless. QV over KT must be dimensionless for the right hand side to match the logarithmic term on the left hand side. Okay. The QV over KT is telling it's dimensionless. It is dimensionless. Why? Because this is a constant. This is a numerical value. Logarithmic of I over I naught over I over I naught plus 1 is also as a numerical. It's a numerical value. It's a numerical value, and this is a constant. So the LHS dimensionless. Also, the QV over KT also dimensionless. It means it is dimension is 1. We can say Q dimension is dimensionless is okay, so is equal to 1. So what is KT? KT over Q is equal to what? It is V. By dimensional analysis, okay, we can derive the term KT over Q is the dimension of V. The KT over Q is dimension of V. So both ways we have derived the term of KT over Q's dimension. It's coming a dimension of voltage. Okay. The 13th question. The variation of rate of decay A of a radioactive sample with time t is given by the relationship is equal to A is equal to A naught into C to the power minus lambda t. The dimension of lambda is, that's what they want to know. The dimension of lambda is what? Okay. For this, as like a previous example, even if you don't know about this equation, by the dimensional analysis, we can derive the dimension of lambda because, okay, what is A? A is the rate of decay. It refers to the number of decays per unit time. A is what? The rate of decay. It refers to the number of decays per unit time. So its unit is t minus 1. So unit is t minus 1. This unit is t minus 1. Likewise, the A naught also, the rate of decay at the initial number of decays per unit of time. So the unit of A and the A naught is equal. So A and the A naught are equal means, what about this one? This C into minus lambda t doesn't have unit, or it is dimensionless. By the exponential, okay, C is constant. C should be constant. The exponential formula, what is that? C should be constant, and the lambda t is variable. Lambda t is variable, but it is still numerical value. Still numerical value. So the numerical value doesn't have dimensions. It's dimensionless. So the lambda t, it's dimensionless. It means 1. So the lambda is, what is that lambda? T minus 1. T minus 1. The lambda, dimension of lambda is what? T minus 1. Okay. Even if you know this equation, or if you doesn't know, you can derive the dimension of lambda. So the answer is option number 2, that is t minus 1. Is equal to root into k over rho. That is, c is the speed and the rho is the density. The units of k, the requirement. The units of k is the requirement. So this question is 2005. So we will multiply, we will square the both sides. We square the both sides. Then what will happen? C squared is equal to k into rho. So means k is equal to what? Rho c squared. Rho c squared. So we know what is rho, kg m minus 3 into c squared is what? M squared. So ms minus 1 is the c, means squared is what? So kg m squared m minus 3. So m minus 1 into s minus 2. So this is the c k's dimension unit of k. Unit of k. So unit of k is, what is the answer? The option is kg m minus 1 s minus 2. The option is 4 is the answer. Option 4 is the answer. Actually, what is kg m minus 1 s minus 2? For you to remember, or for the extra knowledge, this is the unit pressure, unit of pressure, like Pascal, which makes sense because in physics, k in this type of equation often refers to, it's called bulk modulus. K is we call bulk modulus or elastic modulus. It's called bulk modulus or elastic modulus In this type of equations, we are called like that, which has unit of pressure, Okay. The question number 15. Which of the following is not an SI unit? It's very simple question. This is from past paper 2006. Okay. kg is a base SI unit. We know that's mass. SI units of mass. M, we know that is SI units of length. Okay. The S, simple s, also the SI unit of time. A, ampere, is the electric current, the SI unit of ampere, the SI unit of electric current. We are having capital K, that is thermodynamic temperature. But what about this one? This is a small k. This is a small k. So there is no base SI units as small k. We are having capital K, that is thermodynamic temperature. So the answer is option number 5. Option number 5, the answer is not an SI unit. Okay. For you to remember, I just mentioned here physical quantities. Length is meter, mass is kg, and time is second. Electric current is ampere, and the thermodynamic temperature is capital K. Amount of substance, it's mole, and the luminous intensity, candela. Okay. Okay. The next one is, it's from past paper 2007. Okay, the 16th question. The dimension of a certain physical quantity when multiplied by L cube, okay, dimension L cube, yield the dimension of work. The physical quantity would be. So what he is telling, one of the following, okay, one of the following dimension, it's multiplied by L cube, it will be equivalent to the dimension of work. For this, what we have to do, first we have to derive the dimension of work. First we have to derive the dimension of work. So what is work? Work is equal to force into displacement. So the work minus 2 is the dimension of force, and then multiplying by L, that is coming the work's dimension as ml squared t minus 2. Okay, the work dimension is ml squared t minus 2. Okay, now we will derive the dimension by dividing L cube. It is coming ml minus 1 t minus 2. ml minus 1 t minus 2. So we will check one by one. Okay, ml minus 1 t minus 2, what is that? Force? No, force is ml t minus 2. It is not the answer. Momentum also m into L t minus 1. ml t minus 1. It also not the answer of ml minus 1 t minus 2. So what about the pressure? Yes, pressure is equal to what? Force over area. Force is what? ml t minus 2 over L squared. It means what? M L minus 1 into t minus 2. It means if we multiplying the pressure dimension by L cube, it is coming the dimension of work. It is equivalent to dimension of work. So the answer is pressure. Answer is number 3. Answer is number 3. And the mass is capital M. The velocity is LT minus 1. So the answer is option number 3. Okay. So now we can derive a formula. We can remember this formula for your tip. Work is equal to what? Pressure into volume. Another formula. So actually work is what? Work is equal to force into displacement. Okay, force into displacement is what? Work. But also we can use the formula pressure into volume. So this from this equation also we can derive this equation. Okay, the question number 17, dimension of kilowatt hour is what? That is from past paper question 2008. The dimension of kilowatt hour. What do you mean kilowatt hour? Okay, kilowatt, kilo is the prefix, watt is a unit, hour also we can measure as in a unit. So kilowatt hour, watt is what? Watt is we are measuring as a power. Okay, watt is power. Power into what? Time. Power into time. So actually power is what? Work over time. Power is what? Work over time. So power is work over time. And again, we have to multiply the time. So kilowatt hour, it is equal to the dimension of what? Work. Kilowatt hour, the dimension is equal to work. That is energy. That is energy. Energy. That is energy. Equal to the energy, dimension of energy. So the energy is power into time. We know what is the power? Work over time. That is MLT minus MLT square T minus 3. The power from the previous one also we have derived that one. So ML square T minus 3 multiplied by T. The energy, that is work, it is ML square T minus 2. That is the dimension of kilowatt hour or watt hour, whatever it is. It is the dimension of kilowatt hour, ml squared T minus 2. That is the answer is ml squared T minus 2. That is the answer is first is the right answer. The first option is the right answer. Okay. Then question number 18. Energy E of photon of frequency F is given by E is equal to H into F. The dimension of HR. What is the dimension of HR? Okay, that's the question. So we are given the equation of energy of photon is E is equal to H into F. Where E is equal to what? Energy. F is equal to what? Frequency. The dimension of energy we know ml square T minus 2. And the frequency dimension of frequency, what is frequency? F is equal to 1 over T. So the dimension of frequency is T minus 1. So we want to know the H. H is actually Planck's constant. In this formula, H is we are calling Planck's constant. So in that case, we equate these dimensions and LHS and RHS, then we can derive the dimension of H as ml squared T minus 1. Okay, by equating the substitute the dimensions here and equating the dimensions in this formula. By using this formula, we can derive the dimension of Planck's constant, that is ml squared T minus 2. That is answer number 4. 18th answer number 4. Okay. SI unit of the quantity. The 19th question is from year 2010. Past paper question from 2010. The SI unit of the quantity of heat. You should know what is heat. Okay, then you can directly choose the answer without confusion, without any confusions. Okay. In physics, what is heat? In physics, the heat is defined as the form of energy. The form of energy that is transferred between two systems or a system and its surrounding due to a temperature difference. Due to a temperature difference, transferring energy from between two systems or in a system. Okay, transferring energy. So the heat is what? Is energy. We know that the energy we are measuring by joule. Directly we can answer. So heat is a form of energy. It is a form of energy. The SI unit of the energy is joule. SI unit of the energy is joule. Calorie, we are not it's a it's non-SI unit. You know that one. Watt also, but it is unit of power. Unit of power. Watt is also what how we are measuring? Joule second minus 1. Kelvin, it's a temperature actually. But for this, we are not measuring Kelvin. It's using for the temperature, not for the heat. Okay, heat is measured in SI units as joule. So CD candela. Candela is the luminous intensity. Okay, so what we only the thing is we should know the idea that heat is energy. Heat is energy transferred between two systems surrounding due to the temperature difference. Okay, if you know that one clearly, confidently, then you can answer the question easily, in a very short time. Okay. The question number 20. Which of the following does not represent a fundamental unit in the SI unit? Fundamental unit in the SI system. It's from question from 2012 past paper. Okay, for easiness, I tabled those symbols. Okay, meter, m is small m, we are using the quantity of meter, that is fundamental SI unit. Okay, kg also kilogram, also the fundamental unit of SI units. S is second, also using as a fundamental unit. Capital K is a Kelvin, also is a fundamental unit. So the Newton is only the derived SI units. Derived SI units. So the Newton is the answer. Answer number option number 2 is the correct answer. Trick to remember, fundamental units are the base units. Fundamental units are the base units like mass, length, time, temperature, etc. But derived units are formed by combining base units. Combining base units are, we are calling the derived units. This is the trick you have to remember in these questions. Okay, thank you very much. We have completed up to 20 MCQ questions of the from the past papers. We will continue on the next videos also the past paper questions. Okay, thank you very much. Good luck to you all.